Kepler's laws of planetary motion. So by the end of this video, you should be able to describe how Tycho Brahe and Johannes Kepler work together to contribute to our understanding of how planets move around the sun, and explain Kepler's 3 laws of planetary motion. Tycho Brahe was born to Danish nobility in 1546. He was financed by King Frederick II, and he built an observatory in the North Sea island of Haven, Denmark. He made very careful, detailed observations of the motion of planets and stars over time without a telescope over 20 years. So his observations were some of the most detailed and long lasting, like longest time frame, ever by a single person, definitely from a single location and with great detail. He noted the motion of planets were different from what Ptolemy's geocentric model had predicted. So this is where Ptolemy's model is starting to fall apart. It's no longer predicting accurately the motion. So something had to be done to change our understanding. And he wanted to develop a better model using his data, but he just didn't have the mathematical skill to do this by himself. So he found Johannes Kepler. Kepler was born to a poor family in Württemberg, Germany in 1571. He was hired by Brahe to assist in analyzing his data, and they worked in Prague. Brahe wouldn't share all of his data until after he died, because Brahe wanted to develop a new model on his own. He just needed Kepler's help to do it, but he wanted to take all the credit. So after Brahe's death, Kepler was able to access all of the data and was able to see patterns that hadn't been revealed to him before in the data. He developed 3 laws of planetary motion. These laws describe the motion of planets, but they do not explain planetary motion. The explanation of planetary motion came from Newton about 100 years later. Kepler's laws are completely descriptive. So Kepler's first law has to do with the orbital shape. He found that the initial assumptions made by Copernicus and others that planetary orbits were perfect circles didn't fit with Brahe's data. So the new assumption is that planetary orbits are not circular, but elliptical. An ellipse is this elongated circle. It's like a flattened circle. They're nearly circular, but not quite. So Kepler's first law states that each planet moves around the sun in an orbit that is an ellipse, with the sun at the focus of one of the ellipses. And we'll talk about what a focus is in a second. There's one right here. So here is an ellipse. An ellipse has 2 foci. They're kind of like, in a circle you have a center of a circle. An ellipse, the center is actually spread out into these 2 foci. In a circle, the foci are the same point, but in an ellipse, they are separated. We can draw an ellipse by doing this. If you take a piece of paper, make a line across it, the red dot here would represent the very center of a circle, or it would also be the very center of this, which is called the major axis, or also the center of the minor axis. So it's where the minor axis and the major axis intersect. The foci are these 2 points. So you would put like a tack at these 2 points and a string around the 2 points, and then a pencil would make a third. And you just stretch that string, that loop of string, out and draw a line as much as you can while stretching the string out. And it actually creates an ellipse. Another part of this is that this line right here, the line from the focus to the edge of the ellipse, plus this line right here to the other focus, if you add these two lengths together, they always will equal the same, no matter where on the ellipse you are. The flatness of an ellipse, like how flat it is measured by its eccentricity. And a perfect circle has an eccentricity of 0. And then you can see these are ellipses of increasing eccentricity. So this has an eccentricity of 0.2, this one is 0.5, 0.8, 0.9, 0.95, and so on. The closer together the two foci are, the more circular the ellipse is. So when the two foci are in exactly the same place, you have a perfect circle. When they're just a little bit separated, you have a small eccentricity and a mostly circular object. And then when they get very far apart, you have a very flattened circle. Mars orbit. So Kepler studied Brahe's data and found that the orbit of Mars to be slightly eccentric based on Brahe's data. He generalized that the orbits of all of the planets must also be ellipses. The idea that the planetary orbits were not perfect circles was brand new. This was revolutionary, and it took Copernicus's model and made it into something that it wasn't before. So let's look again at Kepler's first law. Says that the orbit of every planet is an ellipse. The sun acts as one of the two foci. So here is the sun at one focus. Here is the other focus where there is nothing. And then planets orbit in this elliptical shape over time. Earth's orbit is not this elliptical. This is an exaggerated ellipse. It is slightly elliptical, nearly circular, but this actual ellipse that's drawn in here is much more eccentric than the orbit of Earth. The aphelion or aphelion is the point farthest from the sun, and the perihelion is where the planet is in its orbit closest to the sun. So this point is close to the sun. The aphelion is further from the sun, and we'll talk about the next law. Kepler's second law has to do with orbital speed and how fast planets are moving as they travel through their orbit around the sun. The orbital speed of a planet traveling around the sun varies in such a way that in equal time intervals, a line drawn from the sun to where the planet is sweeps out the same area in the same amount of time as it would in another place. So let me clarify what that means. The area here for A is the same size, the same amount of area as you have for B. The planet would move from this point, from point 1 to point 2, in the exact same amount of time as it takes the planet to travel from point 3 to point 4. So this time is the same as this time. So in order for the planet to sweep out this much distance, it would have to be moving much faster here than it is moving here. So what does that mean? Planets move more quickly when they are close to the sun, and they move more slowly when they are further away from the sun. Here we have a picture of the sun and the Earth in its orbit in each point, say like on the first of each month. So December 1st, January 1st, February 1st, and so on. So there's a month separating each of these locations. It takes the Earth the same amount of time to travel this distance as it takes for the Earth to travel this distance, and the same amount of time to travel this, same amount of time here, same amount of time here. Notice how as you get further from the sun, the distances traveled get smaller. And then as you get closer, the distances traveled get larger because the Earth is moving more quickly as it gets closer to the sun, and then more slowly as it gets further away. And you can use this to calculate the speed of a planet at any point in its orbit around the sun. Although these calculations involve a lot of math, they involve a familiarity with calculus, so we're not going to do that in this class. But if you had that mathematical ability, you could do that. Then we have Kepler's third law, which deals with the orbital period, the amount of time it takes for a planet to complete one orbit around the sun. Kepler discovered that there was a relationship between a planet's distance from the sun and its orbital period. So the distance from the sun is, they call that the semi-major axis of the ellipse. And the orbital period is the time it takes to complete one trip around the sun. The closer a planet is to the sun, the faster it moves in its orbit. The further away a planet is from the sun, the slower it moves in its orbit. Also, closer planets have much shorter orbital periods, meaning it takes less time to complete an orbit than planets that are further away. So there is some math here. Kepler's third law can get quite a bit more complicated than this, but this is as complicated as we will get in this class. We can express the third law mathematically. As long as we're expressing the orbital period in years, so that's the P, is expressed in Earth years, and the semi-major axis distance, meaning the average distance from the sun, in astronomical units, then we can use this equation. So the square of the period is equal to the cube of the distance from the sun. And when I say distance, I mean if we average how far away a planet is in all of these locations, take like all of them and average them together, we would get the average distance. It would be somewhere between the perihelion distance and the aphelion distance. So here we have a picture that shows Mars. Mars has an average distance of 1.52 AU, and it takes Mars about 1.88 Earth years to orbit the sun. And we will look at how that works in Kepler's third law in a minute. So let's use Kepler's third law with Earth. Earth completes one orbit around the sun every year, and we know that the average distance for Earth is 1 astronomical unit from the sun. That's the definition of an astronomical unit. So the P in our equation is 1 year, and the A is 1 AU. Let's take a look at how that works. So the square of the period, does it equal the cube of the distance? So does one squared is 1, 1 cubed is 1, and for Earth, it works. Let's see if it works with another planet. So we're going to look at Mars. With Mars, we know it completes an orbit around the sun every 1.88 Earth years. What is its average distance from the sun? So we're going to see if this can give us an average distance. So there's our equation again, p squared equals a cubed. So we'll plug in the 1.88 years for the period squared, and that equals the cube of the distance. So I'm going to square 1.88. I put that on my calculator. I got 3.5244. And then we still have the a cubed over here. So I need to take the cube root. So in other words, it's kind of like the square root, except it's the cube root. What number multiplied by itself and then by itself again would give you this 3.5244. You have to do that in your calculator. So the cube root of 3.524, I don't know what happened. It's close, 5. And that is equal to 1.52 AU. And that is really close to what we saw a couple slides ago in the picture. Remember that one, 1.52 is the average distance, and 1.88 is the orbital period. So it works. All right, so just to summarize, Kepler's first law deals with the shape of orbits. Each planet moves around the sun in an orbit that is the shape of an ellipse, with the sun at one focus of the ellipse. Kepler's second law deals with orbital speed and says that the equal areas are swept out in equal time. And Kepler's third law relates orbital period to distance from the sun, and the square of the planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit. And that's it.